right. Oh. No, I'm gonna say, yeah. I mean, I'll start, but. Yes, no, the similar kind of, so it's this actually, Jonathan, it's very nice. Yeah, I probably just in the end. After. I might just go do things start. You know, the path is really tight. I don't really get.
What's up?
For this question,
Mm-hmm.
did we learn it?
Yeah, so we're gonna run that today.
Oh.
Yeah.
Okay, because I was like looking for, what is like those words for it?
Yeah. So the gradient we're gonna learn today. I mean, we just covered uniform series, so we'll do a couple examples of that, and we'll learn gradient today as well.
Okay, thank
Yeah.
you.
Mhm. Okay. Like 30 minutes. I don't know, you're right. No. Huh? How did that go? I was trying to park. And they said, I don't know, they just, I'm gonna be like down here, you want to call me. So, actually, gave me the something, and I figured. The fucking, that's so big. I'm like, yeah, that shit is not right. You know, like, it didn't matter. Like, I was waiting for it. You know what I'm saying? Like, I'm like, well, that's actually crazy, bro, because the first time they just put that the top, and I was already like. And I was really like, I don't know, it's just, I can read key and. That's so much. That's so crazy. Which is must not be nice at all. But we do it all. Oh yeah, I was just seeing that right now. That's actually crazy. Bro, the Lakers were gonna be in that trade, like the three-way trade. And they were thinking about trading Westbrook. That would have been good. Yeah, we should be oh, it is. Yeah, let's start. He was telling me that he started. He said they're sure. Sorry today, like. I'm literally at yeah. I want to see it's one big words. It's the last thing. I don't even know what supposed to do. I don't even know what. You never seen during yesterday during the story bits, so he was gonna send it to me like. I've never seen it. Not from again. It's just he has to. That actually. So. Bro, the Fridays I get like friends and yeah. You have a morning class.
All right, it's 1 o'clock, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good. End of second week. All right, so we're just we're chugging right along. All right, so today I plan to finish the lecture notes on time value of money. So I've gotten a couple questions on the homework, and so you can't do all the homework just yet, but after today you should have all the information you need, especially on that very last problem which asks things about uniform series, arithmetic gradient. Today's kind of the the lecture that you need. Okay. All right, so remember the homework is due on Tuesday by midnight, and so, or 11:59 p.m. And so, after today, you have today, Friday, and then Monday, Tuesday to work on it. But once we go over today, the problems don't take that long. So, it's mostly just kind of a plug and check type one. We'll see. Okay, and so I think that's it for my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and pick up where we left off. And so last thing we saw, let me just go ahead and scroll up a little bit. Last thing we saw before we, right as we ended up last on Tuesday, was this formula right here, right? And so we introduced this idea of a uniform series, where a uniform series is like it's a recurring payment, a recurring benefit that has a uniform amount on each time. Okay, and what we derived last time was a formula that could relate F and A. Okay. And so, the key parts of this formula are, the two types of cash flows that we can, that we're converting between, right? And so what we have from this formula is that F is equal to A times 1 plus I raised to the n minus 1 divided by I, okay? And you'll see that this is a pretty common thing for all the equations that we'll do, right? And so in all the equations that we're going to be looking at in terms of equivalent cash flows, there's going to have two different forms, in those equations, right? And so here we have a future sum. And remember, this A here is a uniform series. And so I think I mentioned this very briefly on Tuesday, but we're going to be going over a lot more of these type of equations today. I think we've gone over two so far. And the way to think about these equations as think of them as like ways that you can convert one form of cash flow to another. Okay. And so for this particular formula, since F is on the left side of the equal sign, this allows us to compute an F value given in A, right? So this is if we have A, this will allow us to convert it to F. Okay. And so I think the best way to kind of illustrate that is with an example. Okay. All right. And so in this example, let's say that, a couple, let's say they just got married and they're looking to save money on a down payment for a house. Okay. All right, and so they make, and so, they're going to take the money that they save and they're going to put it into a high interest bank account, right? And so let's say that initially they're able to put in $5,000 into this account. Okay. And so on day 0, the account has $5,000 to start out with. Each year after that, they're able to put in $7,500 each year. Okay. Okay. And so if we assume an interest rate of 8.3%, what we want to compute is how much money is in the account after 2 years. Okay. Okay. And so this last bit here, because we're looking at it from 2 years, this tells us that our n is equal to 2. Okay. All right. And so, we have a few things going on here. And so, we have an initial deposit. And so that $5,000 there is money that they have today, right? And so that $5,000 is going to be a P. And then each year after that, they're going to contribute $7,500, into the account. And so that $7,500 is a uniform recurring payment. And so we can label that as an A. Okay. And so, usually when I do examples like this in the class, I don't write out the entire problem statement just because, it kind of takes a while. But I'm doing it here just to kind of give you guys a little bit of a strategy that I use when I'm tackling these kinds of problems, right? And so if you've already started the homework, you probably have already seen that, the problems, I try my best to kind of write a story along with each one like this, okay? But the important informations that you need to get out of the word problem are, important when you start doing the calculations, okay? And so one thing I do is that every time I see, some kind of cash value in the problem, I like to circle it, and then I label it for what it is, right? And so far, we've gone over 3 different types of cash flows. We've gone over present sums, we've gone over future sums, and uniform series. And so this $5,000, since it's money that they're putting into the account today, that's a present sum, we'll call that P. And then the $7,500, that's an amount that they're going to put in recurring each year. And so that's going to be an A, okay? All right, and then we have to ask ourselves, what do we want to compute in this problem too? And so what do we want to compute is we want to compute how much money is in the account after 2 years. And so that's a single amount of money that's occurring sometime in the future. And so basically what the problem is asking us to do here is to compute F, right? Remember, F represents a single lump sum of money that takes place somewhere in the future, which in this case is 2 years. Okay. Another thing to highlight is the interest rate. The interest rate is probably going to be somewhere in the problem. For most problems, the interest rate is going to be given to you. With the exception of certain types of problems that we'll go over in maybe 4 or 5 weeks. But for everything, that we're going to be doing now, you can assume that the interest rate's going to be given, okay? And I know I kind of wrote it off to the side, but N is good to highlight as well, okay? Okay. All right, and so since we're looking to compute F, what we need to do is we need to convert each of these cash flows, right, the P and the A to F. Let's have. Okay. Because what's going to happen is that this couple is going to be putting money into their bank account, and then over time that money is going to grow based on the interest rate. Okay. And so let's do each cash flow kind of one at a time. And so let's do the $5,000. Okay. Right. And so for this $5,000, we need to convert this P into an F. Okay. And so what we can do from here is we can look at all the formulas that we have so far and find the formula that involves both P and F. Okay. And so the one that the formula that we have that can convert between these two is our compound interest formula, right? And so we have F is equal to P times 1 plus I to the N, right? So that was kind of the first formula that we went over, our compound interest formula from last time. Okay. And so what this formula says that if we're given P, which we are, and we're given the interest rate as well as N, we just plug all of those things into compute F. Okay, so let's go ahead and plug it in. And so we have a 5,000 for P. Okay. The I here is 8.3%, but remember, we always express it in terms of a decimal. This is going to be 0.083. Okay. And then the N here is 2. Okay, so we have 5,000 times 1 plus or 1.083 raised to the second power. Right, we punch that into a calculator, and what we get is 5,864.45. Okay. All right, and so just that initial investment alone, you know, that's going to grow by about $854, you know, over the 2 years in that account. Okay, and so that's the $5,000. Next, we have the $7,500. We've already established from the problem that this is a uniform series, right? And so we need to convert that A to an F. Okay. Okay. And luckily, you know, because, you know, we just presented it, you know, we have a formula here that helps us do exactly that. Okay? So we're going to use this exact formula here to compute what the F is given the A. Okay? And so what we have is F is equal to A here 7,500. Okay, this here is our A. And then we're going to multiply it by 1 plus I to the N. And so you have 1 plus 0.083 to the N minus 1, all divided by 0.083. Okay. And what this gets us is $15,622.50. Okay. So that's the conversion of our 7,500 uniform series into a future sum. Okay. And so from the yearly contributions that this couple is making, that's how much money is going to be in that account. Okay, and so the total amount of money in the account is going to be just the sum of these two, right? And so we have both the 5,000 and the 7,500. Okay, and so if we add these two together, what we get is 21,486.95. And so this formula here, you know, the one that we went over near the end last time, you know, this is useful just for kind of personal savings, because, you know, a lot of times, you know, if you want to make a big purchase sometime in the future, whether it be house, car, you know, other big purchase, computer. Last year I made the joke of NVIDIA graphics cards being, you need to save up for it, but apparently now those prices are normalizing. And so this is kind of a good formula to have. And so, you know, if you are doing your budget and you say, you know, I can afford to save up maybe like, you know, $100 a month for purchase, right? Then this formula here will tell you, you know, if you put that money into into a high interest account, how much money that you'll have in the future, okay? Just based on how much you can save on that. Okay, any questions on this? Okay. All right. And so that's our F and A formula. And of course, you know, you can also manipulate this formula, right? And so, you know, this formula as it currently stands allows us to compute F given A, but you can swap that too. And so, you know, if you have, you know, if you're given F, but you need to solve for A, you can just kind of manipulate this formula algebraically and get that formula. Okay. Okay. And so for instance, if we can just kind of solve the equation for A, what we get is A is equal to F times. And so we basically just take everything in this bracket here and just multiply it by its inverse on the opposite side. We get I divided by 1 plus I to the n minus 1. Okay. And so this will let you compute a uniform series amount based on F. Okay. And so this lets you solve for kind of the inverse problem. So, let's say that that sometime in the future, you need to save up enough money to buy a car, right? And so let's say F here is the price of a car. Okay. And so let's say that you're going to need a car in 12 months, right? And so, if the price of the car, let's say, is $25,000, then based on the interest rate on your account and based on how much time you have, this will tell you how much money you need to put away each month in order to save up. Okay, so you can manipulate these equations however you need to. Okay. Another manipulation that you can do. So now that we have two formulas, we can substitute one in for the other to get some more relationships, right? Because right now we have relationships between P and F and A and F, right? But it would be great if we have a relationship between P and A as well. Okay? I don't know why it's doing crazy. All right, and so what I mean by that is, in the formula above, we have F. If we plug in F is equal to P times 1 plus I to the n, we plug that in for F right there, right? And we manipulate it a little bit, we can get a formula that relates A and P, right? And so if we do that, we get A is equal to P times I times 1 plus I to the n divided by 1 plus I to the n minus 1. Okay. Okay. And that's a formula there that that gives you the relationship between A and P. Okay. And so this particular formula is useful. And so, a lot of times, if you take out a loan, right, you usually pay that back in monthly installments, yearly installments, right? And so this can tell you, what your uniform payments have to be given a present sum, right? Okay. So we can do a quick example of this one. Okay. And so let's say that you want to buy a new phone, but you don't have enough money in your account. And so you need to borrow some money from your uncle. Okay. And so let's say that you borrow $800 from your uncle to buy a new phone. Okay. And so your uncle wants you to pay him back in uniform monthly payments. Okay. And he's going to charge you 5% interest rate. Okay. Okay. And then he wants you to pay him back over a year. And so since there are 12 months in a year, we're going to have 12 payments. Okay. And so based on this information, you can compute how much your monthly payments are going to be. Okay. All right. And so just like we did in the last problem, let's go ahead and circle the cash flows in this problem. Okay. And so we have the $800 is the only one here. Okay. And so since you needed to borrow that money from your uncle to buy a new phone today, this $800 here represents a P. Okay. Okay. And then based on the problem, what we want to compute here are the monthly payments. And so monthly payments we know are, are uniform series, right? And so anytime you have uniform monthly payments or uniform monthly benefits or uniform yearly benefits, uniform yearly payments, then you're going to be computing A. Okay. And so what we need to do is we need to convert from P to A. Okay. And luckily, we literally just wrote down a formula exactly for this, right? So let's go ahead and plug into the formula above. And so we have A is equal to P here is 800. Okay. And then we have I times 1 plus I to the n. And so remember, we express I in terms of a decimal. So we have 0.05. Okay. Then 1 plus 0.65. Okay. Our n here is 12. So let's go ahead and raise this to the 12th power. Okay. And then in the denominator, we have 1 plus I to the n. And so we have 1 plus 0.05. Raised to the 12th power again, minus 1. Okay. And so we plug all the numbers in for this, and what we get is $90.26. Okay. And so in order to pay your uncle back, you have to pay him $90.26 each month. Okay. This is really useful because if you grew up like me and you did borrow money from uncles that are trying to scam you, and so you can kind of check the numbers like this. Right? And so I wish I had this formula when I was 12 years old, and I had to buy that video game console. My uncle lent me money. He told me how much, and he told me how much I had to pay him each month, and I believed him. But I wish I went back and I did the calculations again like this, just to make sure that he was right. Okay. All right. Any questions on this? Okay. All right. And so, just like before, you can kind of move this formula around right here. And so if you need to solve for P given A, then you can do that as well. Okay, so there are lots of formulas, and you're probably seeing very quickly that the amount of formulas that we're getting is exploding a lot. And so, it's good. If you're writing your notes, make sure to box all these formulas because they're good to remember. Okay, so I'm gonna skip around. If you're following along with the posted lecture notes, I'm gonna skip around just a little bit, just so that it's just so the presentation is a little bit more consistent. And I'm going to go over the final member of what I call the cash flow family. Okay, so we have 3 members so far. So we have present sums, we have future sums, we have uniform series. The last member of the cash flow family is an arithmetic gradient. And so the symbol for gradient is G. G for gradient. All right. And so the idea with the arithmetic gradient, arithmetic gradient shares a lot of similarities with the uniform series in that it represents payments, recurring payments over time, okay? But instead of representing a uniform payment, what arithmetic gradient represents is the fact that oftentimes payments either grow or shrink over time. Okay? First. Sorry about that. I've been lecturing on this iPad for a couple of years now. I still don't know why it kind of just randomly just goes berserk. Okay. All right. And so in particular, what the arithmetic gradient represents are payments that change at a fixed rate over time, right? And so each time period, the amount is either increasing or decreasing by the same amount. Okay. And so I think the easiest way to kind of illustrate this is with the cash flow diagram. Okay. So let me go ahead and draw a cash flow diagram. So 0, 1, 2, 3, 4, 5. Okay. Okay. And so usually, for a uniform series, it would look something like this. Right. And so we have the same, we have arrows that occur at every future time instance, but the arrows would be the same size for each time period. Okay. For arithmetic gradients, it's used to represent the fact that, often payments can go up with time, right? And so we have something that looks like this. Okay. Where between each time period, if we measured kind of the difference in height, right? And so if we measured kind of this distance right here, okay, right? And so the amount that each arrow is growing per time period, that is going to be the same. Okay. And so even though the raw payments are going up with time, the amounts that they're changing are the same. Okay. And that amount that they're changing is given by G. Okay. Okay. And so G represents how much the cash flows are increasing in each time period. Okay. Okay. And so that's the idea with the arithmetic gradient. Okay. And so, of course, we have formulas associated with this, and I don't think we have time to go over a derivation for them. And so I'm just going to give it to you. Okay. Okay, and so just like all the previous cash flows, we have formulas here that can convert between G and all the others, right? So we have G to F, G to P, and G to A as well. Okay. And so I'm just going to give you all three formulas here. And so between F and G, we have F is equal to G divided by I divided by 1 plus I to the n minus 1 divided by I minus n. Okay. And so this formula right here is the G and F formula. Next, we have P and G. Next, we have P is equal to G times 1 plus I the n minus in minus 1 divided by I squared times 1 plus I to the n. Okay. This here is the P and G formula. And then finally we have A and G. So we have A is equal to G times 1 plus I to the n minus I times n minus 1 divided by I 1 plus I to the n minus I. Okay. And so that's the A and G form. Okay. All right, it's kind of good just to kind of, I think just get them all out of the way, just so you kind of have them all in the same place in your notes. But these formulas are good to have, especially in certain situations. But last thing we'll cover today is you'll see you actually don't use these formulas all that much. Okay. And so what are gradients used for? So gradients are mostly used for cases where you expect payments to go up with time. Okay. And so in engineering, a situation where that occurs pretty often is when you have maintenance costs that increase with time. Okay. Okay. And so for a lot of older machines, generally as the parts get more worn out and more used, it's going to cost more money to service those parts, because they're, out of production, or maybe they just require more care, more maintenance, more time, right? And so gradients can be used to represent those situations where, you expect the maintenance cost to go up with time. Okay. Another situation could be, maybe you have a negative gradient, right? And so a negative gradient shows that something is actually going to decrease with time. Okay. And so negative gradients can be used to represent the opposite case, where maybe maintenance costs are actually going to go down with time. Okay. All right, so let's do a quick example just so you can kind of see how this is used in class. All right, so let's say a friend of yours just bought a vintage car, okay? And he wants to set aside money now to cover all the maintenance costs for the next 5 years. Okay? Yay. Okay. Because what your friend knows is that over time, the maintenance costs are going to go up each year. Okay. Okay. And he wants to cover it for the next 5 years. And so based on what he's hearing from the shop, and based on the cost of parts over the next 5 years, this is how he expects the maintenance cost to break down. And so he's kind of summarized it into a table. Okay. Okay. And so in year 1, he expects the maintenance cost to cost $120. Year 2 is going to be $150. Year 3 is going to be $180. Then $210, and then $240. Okay. I know these are very small numbers. Okay, so I know the cost of maintaining a car is even just the car that you drive normally is a lot more than this, and so these are just kind of made up numbers for this problem. Okay. Okay, and so if we assume that our interest rate here is 5%, okay, or in other words, your friend is going to put money into a 5% into a bank account with a 5% interest rate. How much money should he set aside now to cover all of these costs? Okay. All right. So this one's a little bit tricky, and so it's a bit trickier than before, and so we have to kind of do this a little bit carefully. Okay, but first of all, we're going to do the same thing we did before, and so we're going to see what are we trying to solve for. Okay, and so from the problem we see that we're looking to solve for money that we should set aside now, and so what we're solving for here is P. Okay, so that's what we want to do. And so everything that we're going to be computing is going to be converted into P. Okay. 5% is the interest rate. Okay. N is 5. Okay. And then for the cash flows that we're looking to convert, it's not given to us directly in the problem. Here it's actually given to us in a table. Okay. Okay. And so we have to kind of, analyze this table and see, what are the cash flow or cash flows that we need to convert to P. Okay. Okay. So let me do this. And so, we have this cash flow table here, but I think it'll be easier to see if we have it in a diagram. And so even though these are costs, I'm gonna draw the arrows going upwards just because of, just because I drew the line down there anyway, okay? Okay, so first thing I'm gonna draw here is, let's draw the line for year one. Okay, so we know this here represents $120, okay? And then year two, we have 150. Right, 150. Here we have 180. 210. 2. Okay. All right. All right, so fairly straightforward. Okay. And so what we see from here is that, in between each time period, right? So from time period 1 to 2, from 2 to 3, 3 to 4, 5 to 4 to 5. Okay. The costs are going up by the same amount, right? And so, between 1 and 2, the cost increased by 30, 2 to 3, the cost increased by 30, and, and so on and so forth, right? And so that's uniform throughout. And so what we can see here is that costs increased by 30. Each period. And so since the increase is 30, right? Never mind the base amount. We'll deal with that in a second. But since the increase here is 30, this tells us that G for this problem is equal to 30. Okay. Okay. Because remember, G here, and so I think people often get confused between the uniform series and the gradient, right? And so for the gradient only represents just how much it's increasing from period to period, okay? And so even though the flat amounts here are, 150, 180, 210, right? The only thing that we're looking at is the period to period increase, okay? And so the period to period increase in this case is 30. And so that's what we said G, right? But a G is equal to 30 doesn't really tell the whole story here, because, we actually do start, with the year one maintenance cost of 120, okay? Okay, and so I'll call that the base amount, right? Because every year, after the first year, every year has at least $120 worth of maintenance costs. It just, stacks and increases it by 30 by each one, okay? And so the way that we can actually represent this is with a uniform series, okay? And so if we say A here is equal to 120, then these two things combined will kind of represent this entire cash flow, right? Because I can do this, right? And so, even though these are, 150 to 180, and so on and so forth, I can do this, right? And so for every time period, I can draw an arrow that's the same size as the one that we began with, and each of these are going to be 120, right? And so what you can see is that underneath it all, you have a uniform series of 120, and then we're adding a gradient of 30 on top of that, right? And so we actually have two cash flows here that we need to convert. We need to convert this A to a P, and then this G to a P as well, okay? Okay. Does that kind of make sense how that kind of broke down between those two? And so oftentimes, you're not just going to see an arithmetic gradient by itself. It's always going to be an arithmetic gradient and a uniform series together. Okay. And so being able to take a situation like this and kind of pull both apart is important, so you can kind of recognize those patterns. Okay. Okay. And so from here, the procedure is pretty standard. And so we have formulas that convert, A to P and then G to P. Okay. And so we can just use those formulas. Okay. All right, and so for A to P, what we have is P, we'll call this P1. P1 is equal to A times 1 plus I to the N minus 1 divided by I 1 plus I to the N. Okay. All right, so that's A to P, and then now we need G to P, and so we have P2 is equal to G times 1 plus I to the N minus I times N minus 1 divided by I squared 1 plus I to the N. Okay. All right, and so we have everything that we need for these formulas. We have both A and G that are in pink and green above. All right, we're given the interest rate. We know the N here, N is 5. And so we can just plug and chug, right? And so we plug in for this one, and what we get is P1 equal to 520. And this one, P2 is equal to 247. Okay, we add them together. The total P is $767. Okay. And so if your friend sets aside $767 into a bank account with a, what was it, 5% interest rate, then you know, they'll have everything that he needs for all the repairs. All right. Any questions on this example here? Yeah. P2 equation, this is for P and G, right? And so if we look back up here, it's this formula right here. Right. So if we're given G, then we can use this formula to compute P. Yeah. Oh, the P1 equation. P1 is from the P and A equation, which was this one here, but we inverted it. And so, you know, we see that this formula here has both A and P. And so we basically took everything in the bracket here and then moved it over to the other side of the equation. Yeah. Any questions on this example here? Okay. Actually, let me do this one, please. I think the other thing would be easier to explain. Okay. All right, so you know, so far, you know, mostly today, you know, we've gone over all these very complex equations for, you know, all of these different pathways, right? And so, you know, these are very, you know, they're not hard per se, they're just really kind of annoying to plug into, right? And so, you know, people realize this, and so, you know, especially if you're doing with working with very complex engineering projects with complex financials, you know, using all these formulas all the time can be very, very cumbersome. And so, you know, what people did was that they found a better way, not a better way, but a more convenient way to do a lot of these calculations, which really helps if you're doing them on, right? And so I want to make sure I cover this today because you can use this method on the homework. And then the other topic I want to go over, I think, is not going to be until the next homework. Okay. All right, and so the thing I want to go over today are the compound interest tables. Okay. And so if you've been to our course website, you might have seen this on the front page, and I'll show you how to use them in a bit. Okay. Okay. And so the whole idea with the compound interest tables is that using formulas to convert cash flows can be very cumbersome. How that happens. What the heck? Okay. If you're doing just one or two, it may not be that bad, but you'll see there are situations where you need to do many conversions to be quite in, okay? So what people did was they tabulated a lot of the important conversions. Because all these formulas are, and I've been saying this all throughout the day, all these formulas are basically just conversions, right? And so we have one type of cash flow and we want to find its equivalent cash flow in a different form. Okay? Okay. And in fact, it goes even deeper than this, right? And so let me write out, one formula that we had from the previous example, and I'll kind of highlight some features of it for you. And so let's take the P and G formula. And so we have P is equal to G times 1 plus I raised to the n minus I times n minus 1, okay? Divided by I squared times 1 plus I to the n. Okay. So this is about as cumbersome as you can get, right? Because we have, i's everywhere, n's everywhere. There's a square down there. There's a fraction. And so, it's kind of a mess. Okay? Let me do this. And so let me go ahead and divide both sides by g. And so, we have p over g on the left-hand side. Okay, so we have p divided by g. Okay. And so if we divide the right-hand side by g, the g is going to cancel out. And then all we're left with is, say all, but, it's quite a lot. So 1 plus I. This stupid iPad will cooperate. Okay. And so what we get is P over G is equal to 1 plus I to the n minus I n minus 1 divided by I squared times 1 plus I to the n. Okay. All right. So that right-hand side is still kind of a mess, right? But, if we look at the variables that actually show up on the right-hand side, okay? First of all, we have I, right? And we have n, okay? So those are the only two variables that we actually have there. Everything else is either a 1, a 2, which are just constants, which are kind of always there. Okay? And so what people found, or what people kind of realized that, because everything here is just based on I or n, what if we just built tables out of these and then, compute these for all different combinations of I and n, okay? Okay. All right. And so that's what the compound interest tables represent, okay? And so, I'll give you kind of a quick preview of what it looks like, and then I'll show you how it actually looks from the website. Okay. Okay, so the way it works is that, there are lots of different tables. And so if you download the compound interest table from Canvas right now, you'll see that it's like a 21-page document, okay? And each page there represents a different interest rate, okay? And so, let's say that we're looking at the table for I is equal to 5%, okay? And so the way it works is that if you look at the tables, okay, it's going to look something like this. Okay. Okay. And so in the very first column there, you're going to see n, which are the, the n that you would plug into the equation. And then every column after that all of these are what I call, conversion factors, okay? Okay. And so those are what you need to multiply, your equation or your cash flow by in order to convert it from one to the other, okay? And so, for example, let's say that we're looking at this column right here, okay? This is our P over F column, right? And so what this column here gives is these are the conversion factors that convert from F to P, okay? Okay. And so since F is in the denominator here, that's what we're converting from. And then P here is in the numerator, that's what we're converting to, okay? And so what you can do is that, if you have a cash flow problem where your interest rate is one of the tabulated values, you can just use these table values instead of using the formulas. Okay. And what you'll see is that it makes the computations a lot more convenient. Okay. Okay, so let me do an example here just to show you how it is. Okay. So let's do the previous example, but let's use the tables instead of those really cumbersome formulas. Okay. And so if you remember from the previous example, right, that was our example with our friend buying the vintage car. We had two cash flows that we needed to convert. Okay. Okay. And so first thing we needed to convert is we needed to convert an A is equal to 120 to P, okay? And then we also needed to convert G is equal to 30, and we need to convert this to P as well, okay? And so let's see how we actually do this with the compound interest tables instead of actually, doing the formulas, okay? Okay. And so what do we know? And so here we know that I is equal to 5% and N is equal to 5 years, okay? Okay, so let's compute P1 first, right? So P1 is the present day cost of the A is equal to 120, right? And so the way that we can do this with the tables is we say that P1 is equal to A times P over A, okay? Then we put in the interest rate, and so the interest rate here is 5%. And the N value here is 5, okay? Okay. And so basically this thing that I have in parentheses here, this is what we're going to look up in the table. Okay. And P2 here is going to be G. And since we're converting from P to G, what we need is a P over G factor. Okay. The I here is 5%, and the N here is 5. Okay. And so just like in the previous one, we're going to look this up in the table. Okay. Right, and I'll show you how to do that in just a second, right? And so what I have on this console computer here is I have the course website loaded, and so I'll show you how you actually look these up in the table. Okay. But before I kind of switch, so I'm going to switch screens here. So I want to make sure everyone has this written down. And so does anyone have any questions on this? Okay, all right. So let me go ahead and share my screen here. Okay. All right, so here is the course website. And so if you go to the home page on the course website, you'll see that there is a link here for the compound interest tables, right? And so let's go ahead and click on this. Okay. You can, of course, download it, and I highly suggest that you download it to your own computer, okay? And so what you see here, oh, it's actually a 32-page document. It's a 32-page document of a lot of these numbers, okay? Let me kind of zoom in a little bit, so it's a little bit easier to see, okay? And so what you'll see is that at the top left corner here of each table is the interest rate for that table, right? And so it starts out very small, and so it starts out at 0.25%, okay? And so first thing you need to do is that, considering the interest rate that you are working with, is to go to that table. And so for this particular problem, we had an interest rate of 5%. And so let's go ahead and scroll down. Wait for it to load. And we're going to go to the table for 5%, okay? Right, and so you can see here that we are at this table here, 5%, right? And so we're good. All right, next thing you need to do is you need to find the row for the n that you're looking at. And so here we have n is equal to 5, okay? And so we're going to look at the 5th row, okay? And so the last thing you're going to need to do is you need to look up the conversion factor that you need, okay? And so here we needed 2 conversion factors. The first conversion factor was a P/A factor, okay? And so we make sure we're on the right interest rate, we're on the right row, and we look at the column for P/A, okay? And so here that conversion factor here is 4.329. And then the other conversion factor that we need is P/G. And so the P/G factor here is 8.237. Okay. All right, so let's take these conversion factors and bring it back to the example that we were working with. And then see and then look at the results. Okay, so I'll write it down in a second, but I wanted to show you kind of how this is done. Okay. Let me come back here. On the screen. Okay, so based on what we looked up in the table, so this P/A factor, right? This P/A factor for 5% and 5, we saw that this was equal to 4.329. Okay. And then this P/G factor for 5% and 5 is 8.237. Okay. Okay, so let's go ahead and put all this together and solve for the final result. Okay, so the final result here is going to be A. So A here is 120. Okay. Okay. Let's plug in the conversion factor that we looked up in the table, which is 4.329. Okay. Then we add that together with G. G here is 30. And then we're going to multiply it by the conversion factor that we got from the table, which is 8.237. Okay. So that's our P/G. And so we add these together, and what we get is $767. Okay. Right. And so using the compound interest tables, we were able to get the exact same result as we did before, just without using all those cumbersome, formulas, right? Okay, and so for most, I'd say most of the students that I've taught this class for before, most people prefer to use the tables, just because these formulas, especially if you're working on a calculator, can be kind of annoying to put in. And so for me, I don't mind either one. And so whether you prefer the tables or whether you prefer the formulas, it's up to you. Okay. The only thing that you have to be careful about is that, the tables here don't cover every single interest rate. Okay. Okay. And so there will be situations where you're given an interest rate in the problem and there's no table for that, right? And so I think the first example that we did today, the interest rate was 8.3%, okay? And so I'll tell you right now, there is no compound interest table for 8.3%. And so for those situations where your interest rate is not in a table, you're going to have to use the formulas for that. So, that's kind of unavoidable. And so that's why I kind of, show you both. And so that, if you can use the tables, that's great. Go ahead and do it. It's a lot more convenient. It's going to save you a lot of time. But there will be situations where you need to use the formulas as well. Okay? Okay. Right, and so it's good to have kind of both in your arsenal, so that for any interest rate, you're kind of ready to go for that. Okay. All right, any questions on this? And for the exams as well. And so for the exams, I'm going to print out, I'm not going to print out the entire 32-page document for everyone. That's just ridiculous. But what I'll do is I'll probably limit the interest rates on the exam between 2 or 3 different interest rates, and then I'll give those to you on the exam as well. So the compound interest tables will be available for you on the exam. Okay. And so the last thing I want to go over today are what I like to call standard forms for these cash flows, and what happens if you get a cash flow that's not standard form. Okay. And so I think this is something, we'll probably start today. It's 2:08 already, and we'll probably finish this up on next Tuesday. Okay. And so up to this point, we've covered the 4 different forms of cash flow, right? And so we have, present sums, future sums, uniform series, arithmetic gradient. Okay. And so each of the 4 each of the 4 cash flows has what I like to call kind of a standard form, or a standard way that it's meant to be presented. Okay. Okay. All right, and this is kind of best shown visually through the cash flow diagrams. Okay, and so let's kind of go over each one. Okay, so let's go over present sums. And so present sums, I think, are the easiest. Okay. Okay. And so present sums are just single sums of money that occur, that are occurring today, right? And so the standard form of present sums are that, the cash flow occurs on year 0. Okay. I keep saying year, but you can say time period 0, time period instead of year would be more general. Okay, but I'll just go there. Okay. Future sums are single lump sums of cash that occur at some point in the future. Okay. Right. The key here is that there's only one. Okay. Okay. All right. So present sums, future sums, I think those are fairly straightforward. The only thing you have to remember is that those are just single cash entries. Okay. And the arrows can go up or down. I'm just putting them down right now just to be consistent, but they can go up as well. All right. Where things get tricky is with arithmetic gradients and uniform series. Okay, so let's do uniform series first. Okay. And so uniform series, remember, this is a recurring cash flow that occurs at all points in the future, but its standard form is that it actually starts on time period 1. Okay? Okay. And this part right here is really actually important. So it may seem kind of like a minor point in the definition, but that's kind of what the standard form is defined as. Okay. Okay. And so, a uniform series would look something like this. Okay. And so all the arrows would be the same size, but the key here is that the standard form kind of starts on year 1 right here. Okay. Keep saying year. It would be time period 1. Okay. Okay. And so for arithmetic gradient, remember, this represents a recurring increase or an increase in recurring cash flows. Okay. And the standard for this one, which I think throws a lot of people off, is that this actually starts on year 2, or the first time you actually see an arithmetic gradient increase is on year 2. Okay. Okay. And so if you were to draw just an arithmetic gradient just by itself, you're going to have nothing. You're going to see nothing for time period 0, nothing for time period 1. And then 2 is when you're going to start to see things that are increasing. Okay. Remember, this increasing amount is G. Okay. Right. And the reason for that is, remember, gradients only represent how much they're actually increasing. And so anything that you have in year 1, right? Anything in year 1 is considered the base amount. And then the gradient just kind of adds on top of that. Okay. Okay. And so why am I telling you this? And so why are we going over these standard forms? Okay. The most important thing, and we'll expand on this on Tuesday, is that when you perform conversions between different cash flows, the implicit assumption is that all the conversions take place, between these standard forms. Okay. Okay. And so if you're using a formula, you're using a table, the assumption is that, the P that you're using and the A that you're converting to, it's always going to be in these standard forms. Okay. Which may not be the case. And so you might have situations where your cash flows don't exactly match these patterns. And so on Tuesday, we're going to revisit this idea, and then we're going to see what you need to do when you do get cash flows that are trying to follow weird patterns. Okay. All right, thank you everyone for coming today. Remember the homework is due on Tuesday at midnight, so make sure you are working on it. If you have any questions on that, just shoot me an email and I'll be happy to answer. But besides that, have a great weekend, everyone, and I'll see you guys on Tuesday.
Oh, God. Last one? Yeah. Yeah. I was in there a lot of. Oh, my. This is,
Oh,
they're wrong.
you might know if I don't.
Why?
Oh, that's fine too.
That's fine.
Yeah, but just show some of your MATLAB scripts and just how you kind of set that up. Yeah.
Do you want me to attach my?
Yes.
Files too?
Yes, if you could put it all just in one file, like just convert the MATLAB code to PDF and then attach that, and that would be good.
Oh, I never attach on the Word.
Oh, okay.
Try to like.
Yeah. So if you go into MATLAB, you can click save as a PDF, right? And so if you go to online and search merge PDF. And so you have the homework that you scanned and then you have your code from MATLAB, and then you can go to any of these will work.
Oh,
I feel like it's a different one every time. And then if you go here, then you can load multiple PDF files and then you can merge them together into a file.
because I think I use a C
Okay.
thing.
Oh, okay. Oh, if you're doing snipping, then you can put it into a Word document and then
Okay,
and then convert that to PDF.
okay,
Yeah.
thank you.
Mhm. All right, any final questions before I close up the Zoom? Okay, all right, so see you guys Tuesday.